Welcome back to my math YouTube channel. So today I want to talk about the derivatives. So far we have covered the integrals. Now I want to go back and talk about the derivatives. Guys, here I'm not really trying to give you like a rigorous proofs of things, but I just want to give you some definitions, some basic definitions, some basic rules for derivatives, and then we're going to use those rules to actually do problems or solve problems to find the derivative of different types of functions. There's a lot of different rules. We'll start with the simpler ones, the basic ones, and then we'll try to do more complex and more challenging ones. So guys, the idea of finding a derivative is like more of, you can kind of relate it to the idea of finding the slope of a tangent line. So in algebra usually, or pre-calc, we usually talk about finding the slope of a line given 2 points, but here the idea is more about finding the slope of a tangent line, and it's mostly finding that slope of that tangent line at one particular point, which that is what makes it more interesting, and that is what makes it unique and different than any other course like pre-algebra or algebra or geometry in general. Okay, and then you can also think of the derivatives if you like to think in terms of the physics. It's also like instantaneous velocity at a particular point of time. Okay, so that's the basic idea of a derivative. As I already said, I'm not really trying to define or discuss this whole idea of derivative in this video or in these videos. Or rather, I want to like talk about the rules and use the rules to solve examples here. So the very first basic rule is called the power rule. So let us try to look at the power rule carefully. Guys, the power rule is the power rule for derivatives is how to find the derivative for a function of the form x to the power n, and n can be an positive integer, a negative integer, it can be a rational number, irrational number, it does not matter, it's going to work out. Okay, so the notation for derivative is, there's two notations actually. One is called the prime notation and other one is called the differential notation. The prime notation is usually like, if I have a function f of x, let us say f of x is x to the power n. Guys, the prime notation looks like this, f prime of x, and then the derivative notation is more like d over dx of the function f of x. That is the derivative notation, and this is the prime notation. Okay, guys, these are the most generally used notations are for finding or writing the derivatives. Now coming back to our power rule, guys, the derivative of this a function of the form x to the power n, and n can be anything from integer to negative integer to positive and rational or irrational number. So guys, the derivative of this function, so d over dx of x to the power n, is simply n times x to the power n minus 1. So just looking at this, let us see what is going on here. So whatever the exponent is, it just comes in the front, and then it's times x to the power n minus 1. You're just taking 1 away from the exponent. That's how I like to remember this. Now, if you are wondering like where does this formula come from, guys, there's few different ways of actually getting this formula. One of the ways is actually to go back and look at the basic limit definition, how to calculate derivatives using the limit definition. So one can use that, and most of the textbooks actually have that. Most of the calculus textbooks actually have that whole proof of how to use the basic idea of the limits, which I also like to call as the first principle to finally get this the derivative of this function equal, or the power rule in general. So guys, it is easier to do it for like positive integers, but when it comes to the rational functions, then it gets a little bit tricky, but can still be done. But guys, here again, I'm not trying to verify all that using all the rigorous proofs. All I want to say is that this is the power rule, and we can let us quickly look at this power rule and try to make some sense out of this for some simple values for n, without going into the limit definition, without going into a lot of the details. So guys, one of the things that I would like you to notice here is, let us talk about some simple examples. Okay, so thinking through some simple examples, and we can see a pattern going on here. Guys, let us look at if I have, let us start with a function like a constant function, a simple function. So let's say I have f of x equals to 1. I can also think of that one as x to the power 0, right? X to the power 0 is 1. So what is the derivative of this function? So if I have to take the derivative of this function, we know that the derivative of a constant function, and if we don't know that, then guys, we have to go back and look at the limit definition on all that. Or it's not too complicated to actually see the derivative of an constant function like 1, because keep in mind the derivative is the slope of the tangent line, and if you think of a line which is y equals to 1, it's just that horizontal line, right? So the slope of this horizontal line basically is going to be 0, right? So the derivative is just simply 0 for the constant function. So it is going to be the case for any constant function, right? Because it's always going to be a horizontal line, and slope of that horizontal line is just 0. Then moving on to something more fun, more interesting, is like just a linear function x. So guys, for a linear function x, again, think about the slope. The slope is, we can actually use the limit definition to actually calculate that slope of the tangent line, which is in turn the derivative of the function. We can do that. Or if you just think about this like idea of a linear function y equals to mx plus b, the coefficient of x, which is m, is the slope of that line, right? In this case, what is the coefficient of x? It's just that invisible 1. So we can say that the derivative, because derivative is the slope of that tangent line, right? So it is going to be just 1. But guys, I'm going to, instead of writing it like 1, I'm going to write this as x to the power 1 first, and then I'm going to rewrite this 1 as 1 times x to the power 0, right? Because x to the power 0 is 1, 1 times 1 is still 1. I'm doing all this so that we may be able to see a pattern. And guys, there is a pattern here. So we can also rewrite this as 1 times x to the power 1 minus 1, right? So I will circle the things that I would like you to see. That is this one. And then guys, let us move on. Let us look at what about the quadratic function. So for the quadratic function, yes, we may not be like, there's no like quick and easy way of finding the slope of the tangent line. So one may have to go back and use the limit definition. So guys, using the limit definition, which I'm not using here, I'm just writing the final answer. So guys, if you use the limit definition on this guy, then the derivative comes out to be 2 times x. So guys, here again, I'm not trying to like use a rigorous method of proving this. We're just trying to look at this, if there's any pattern, so that we can at least see that, okay, this looks like familiar, and this seems like a reasonable formula to calculating the derivative of functions of the form x to the power n. And this is 2x, and allow me to rewrite this as 2 times x to the power, how about 2 minus 1? Because 2 minus 1 is just 1, so it's the same thing, right? So let me circle that one. Let me do one more. So guys, what about if I have fx equals to a function, a cubic function? So if I have a cubic function, the derivative, again, there's no like a direct easy way of doing it. We have to use the limit definition for now, or some other ways, but it's all going to be a rigorous method. So I already have that. So it is equivalent to 3x squared. And I can rewrite this as 3 times x to the power 3 minus 1. So guys, I'm going to stop here, and finally, just let us see if there's a pattern here, because my goal finally is to evaluate the derivative for a function like x to the power n. Of course, we are using integers here, so we cannot generalize this that it's going to work for all the n's, but at least we can see that it works for integers, okay? Which is like which is the power rule, but it's not only specific for integers, it works for all the values for n. So here, if I look at the pattern here, guys, we can see that what is happening. Let us first look at this. When I have an x cube, so 3 comes in the front, but 3 is that exponent right here. And then what is happening to the exponent right here on the right hand side? You're reducing by 1, right? Because this is the actual answer, so it can be written as 3 minus 1. Now let us see if that is true or valid for all of these cases. When I look at the second one, when we have an x squared function or a quadratic function, again, the 2 comes up front, but what is that 2? That 2 is the exponent of the original function. And then there's again 2 minus 1. Okay, there was a 3 minus 1, there's a 2 minus 1. We can already see there is some like a pattern going on here. Let us verify it for the first linear function. Again, we can bring that 1 up front, like we did in this case. We got the exponent 2 in front, 3 in front, and then we have 1 minus 1 again, like we did here, right? So looking at this pattern, we can say that for x to the power n, we just have to bring the exponent n in the front, like we did in these 3 cases. And then x to the power what? Simply we're subtracting 1 each time, so n minus 1. So guys, that is what the power rule is. Yeah, we just verified it for some of these integers, which we can see it works for those integers, but it also works for the other rational functions and other functions as well. Okay, so guys, that is number 1. That is our power rule. Then I also want to quickly talk about the other few quick rules, like simple rules that we are going to use for doing these examples. So guys, the second rule that I quickly want to talk about in this video is like if I have to find the derivative of the sum. So if I have to find the derivative of a sum, so it could be f of x plus g of x. These are two functions. They should be differentiable at x. And this can be simply written down as the derivative of, you can just break it down. Again, I'm not showing you the whole proof of this, but guys, again, we can use the limit definitions to actually verify this as well. So if you have to find the derivative of a sum, so here I'm just using two functions. It could be 3, 4 or more functions. It does not really matter. All you have to do is you have to find the derivative of the each individual function. So it is just going to be the derivative of the first function plus the derivative of the second function. Actually, if I'm going to add a minus here as well, because it is valid for both when we are adding two functions or we're subtracting functions. You're just going to break it down and take the derivative of each function and then add them or subtract them depending on what we are doing here. Guys, that is number 2, very important. And I also want to talk about number 3 in this video, so that from next videos we can just talk about like just do examples and use these things to actually solve examples. Guys, number 3, which is very important as well, is if we have to find the derivative of something which is like a constant times a function. Again, it's not too difficult to actually do that. You can use a limit definition to actually verify this. So what happens when you are finding the derivative of any constant? So C in this case is a constant, is a number. It can be positive, negative, a rational, irrational number. So what happens here, guys, the constant just comes outside. So it does not really matter. So it just comes outside and then you just have to multiply by the derivative of the function f of x. So that is what we have to do if we have a derivative of a constant times a function. You just take out the derivative and you find you multiply that with the derivative of the function. So guys, these are the 3 basic rules for derivatives. Although we did not rigorously prove it here, that's not what I wanted to do in these videos. I just want to like have these formulas, these rules. Although we were able to at least have a feel for like why this is valid, and we were able to see a pattern, and we verified kind of that this is valid. And then guys, these are kind of obvious rules, but again, we can verify them using the limit definitions. But now we have them, we're going to use them to solve some examples. Okay, but just guys, keep in mind in simpler terms, finding the derivative is like finding the slope of a tangent line, or also you can think of that as it's the instantaneous speed or velocity at a particular time. Okay, so guys, just make a note of these 3 simple rules, and I will see you in the next video with examples. Till then, take care.